August 29, 1907, 5:28 p.m. High above the St. Lawrence River, a worker named Beauvais drove rivets into the great southern span of the Quebec Bridge. Beauvais paused. Something wasn't right. A rivet he'd driven barely an hour earlier had snapped clean in two. In 4 years of construction, he'd driven thousands of rivets. They didn't just snap. He called out to his foreman, his voice carrying across the lattice of beams and girders. Then he heard it. The scream of twisting metal. Not the groan of steel under load, which every bridge worker knew and accepted. This was different. This was the sound of 15,000 tons of iron giving up, surrendering to forces it could no longer resist. The sound of mathematics catching up with ambition, the sound of pride meeting gravity at terminal velocity. The giant cantilever dropped out from under him. In 15 seconds, the southern arm and part of the central section of the Quebec Bridge collapsed into the St. Lawrence River with such catastrophic force that people in Quebec City, 10 kilometers away, believed an earthquake had struck. The impact sent waves crashing against both shores. Debris fountained 200 feet into the air. And 75 men, most of them between 20 and 35 years old, died in what remains the worst bridge construction disaster in human history. But this story doesn't end there. This bridge would kill twice. 9 years later, after the disaster had been investigated, after blame had been assigned, after a completely new bridge had been designed with 3 times the safety margin, after every lesson had been learned and every precaution taken, the Quebec Bridge would collapse again. 13 more men would plunge into the St. Lawrence, and this time it would happen in front of 100,000 spectators who had gathered specifically to watch the engineering triumph. The Quebec Bridge was conceived in ambition, designed in arrogance, built in negligence, and completed in blood. It was supposed to be the longest cantilever bridge in the world, an engineering marvel that would make Quebec City an economic powerhouse. Instead, it became a case study in how not to build anything, a monument to the consequences of choosing economy over safety, pride over prudence, and blind faith over basic mathematics. This is the story of how men tried to build the world's greatest bridge, without anyone qualified to oversee it. How warning signs were ignored until it was too late. How a telegram sent to stop work arrived 4 hours after the bridge had already fallen. And how, even after learning every lesson at the cost of 75 lives, they made nearly the same mistake again. The mathematics of destruction were already loaded into the steel. But the warnings would come. 3 weeks before the collapse, a young engineer would notice something impossible. Steel bending under its own weight. His telegrams would grow more desperate. His measurements more alarming. And 700 miles away in New York, the man responsible would dismiss every warning until the very day the bridge fell. We'll get to that. 1887. Quebec City faced an economic crisis. The St. Lawrence River was the city's lifeline during summer months, when ferries could operate freely, carrying goods and passengers between Quebec City and the South Shore. But for 5 months every winter, ice locked the river solid. Commerce stopped. The railway on the South Shore might as well have been on another continent. Montreal, with its year-round railway connections, was pulling ahead economically. Quebec City needed a bridge. The problem was physics. The St. Lawrence at Quebec City was nearly half a mile wide at its narrowest point. The river was deep, with powerful currents and ice flows that could crush anything in their path. Conventional bridge designs required piers sunk into the riverbed at regular intervals, but each pier in the St. Lawrence would cost a fortune to build and would face constant assault from winter ice. The solution was a cantilever bridge. A single massive span reaching across the river, anchored on both shores, with minimal infrastructure in the water itself. Only one other bridge had attempted anything close to this scale: the Firth of Forth Bridge in Scotland, completed in 1890, with 2 spans of 1,710 feet each. The Quebec Bridge would be longer. It would be the largest structure of its kind ever attempted. It would be an engineering wonder of the world. In 1898, after 11 years of planning and financial struggles, the Quebec Bridge Company finally had enough backing to move forward. They needed an engineer, not just any engineer, but one with the prestige and experience to design something never before attempted. They needed someone who understood cantilever structures, who had built major bridges, who commanded respect in the engineering community. They chose Theodore Cooper. Theodore Cooper, age 59, one of America's foremost bridge engineers. His reputation was immense, his confidence even larger. The Canadian Encyclopedia would later describe him as a proud, even arrogant man. That word cheapest would haunt him. The original design called for a span of 1,600 feet, which would require piers in the river at specific intervals. Cooper, looking to reduce costs, made a fateful decision. He lengthened the span to 1,800 feet. This allowed the piers to be built closer to shore in shallower water, where construction would be easier and cheaper. The change added 200 feet to the longest cantilever span ever attempted. It pushed the bridge beyond any existing engineering data. Every calculation would be extrapolated from smaller bridges, with assumptions piled on assumptions. But Cooper was confident. He had built bridges for decades. He knew what he was doing. Robert Douglas, a Canadian government engineer assigned to review Cooper's specifications, saw the problem immediately. The longer span required dramatically higher stresses in the structural members. The compression cords, the massive pieces running along the bottom of the bridge that bore the structure's weight, would be operating at the absolute limits of known engineering tolerances. Douglas criticized the design in his official review. Cooper dismissed the concerns. November 19th, 1900. Cooper was officially retained as consulting engineer for the Quebec Bridge. Shortly after, the Quebec Bridge Company received financial support from the Canadian government. The project was real. Construction could begin. Cooper made several modifications to the standard Canadian bridge specifications, putting his personal stamp on the design. 2 changes would prove critical. First, he reduced the wind load calculations from 56 pounds per square foot, the standard established after the Firth of Tay Bridge disaster, to 30 pounds per square foot. Second, he increased the allowable working stresses in the structural members mores to 21,000 pounds per square inch under normal loads and 24,000 pounds per square inch under maximum loads. Both changes made the bridge cheaper to build. Both reduced the safety margins to almost nothing. Peter Schlapka, working under Chief Engineer J. Sterling Deans at Phoenix Bridge Company, began the actual design work in accordance with Cooper's specifications. All plans would be forwarded to Cooper in New York for review and approval. Cooper, citing health problems, refused to visit the construction site. He would oversee everything from his office, relying on drawings, telegrams, and his faith in Phoenix Bridge Company's expertise. The Royal Commission would later write that this decision resulted in loose and inefficient supervision of all parts of the work. October 1900. Construction of the approach spans began. October 1904. The anchor spans were approved. July 19th, 05. Construction of the superstructure began with a contractual deadline of December 31st, 1908. Any delays would cost Phoenix Bridge Company $5,000 per month. The pressure was on. The timeline was tight. The specifications were already aggressive. And the engineer ultimately responsible for the safety of 86 workers was 700 miles away in New York, trusting people he'd never met to build something that had never been built before. Then someone noticed a problem with the calculations. Schlapke had determined that the actual weight of the fabricated steel was coming in much heavier than his estimates. He had based his dead load calculations on the 1,600-foot span, then extended the bridge to 1,800 feet without updating the weight assumptions. The bridge was going to be 18% heavier than the design calculations assumed. 18%. This number would haunt the investigation. Later, when the Royal Commission examined the wreckage, they would discover that this single miscalculation guaranteed the bridge's failure from the moment construction began. But that revelation was years away. For now, they just kept building. On most bridges, an 18% weight error would have been catastrophic. The entire design would need to be recalculated, probably scrapped and started over. But Cooper had already committed. Phoenix Bridge Company had already begun fabrication. The anchor spans were already in place. Starting over would cost millions of dollars, destroy reputations, possibly bankrupt both the bridge company and Phoenix. Cooper made a decision. He accepted the heavier loads and the increased stresses as being within acceptable limits. The high stresses he'd already designed into the bridge would just have to go higher. They would proceed. The Royal Commission would later examine this decision in detail, comparing the assumed dead loads to the actual weights. Their report stated, "The difference between these two sets of concentrations indicate a fundamental error in the calculations for the bridge. In a properly computed bridge, the assumed dead load concentrations upon which the makeup of the members is based should agree closely with the weight computed from the dimensions in the finished design and with actual weights." But by the time this error was discovered, a large portion of the fabrication had been completed. Turning back was economically impossible, so they built forward onto a bridge that was already failing before the first beam was raised. By 1904, the southern half of the structure was taking shape. From the Quebec City shore, massive steel arms reached out over the St. Lawrence. The cantilever design was visible now, the anchor arm secured to shore, the main span extending outward, supported by nothing but its own carefully balanced geometry. It was beautiful. It was massive. It was doomed. The workers didn't know this. The 86 men climbing the steel structure every day, driving rivets and bolting connections, trusted that someone had done the math correctly. Many were Mohawk steelworkers from the Kanawake Reserve near Montreal, famous throughout North America for their fearlessness at heights. They called themselves skywalkers. They had built bridges and skyscrapers across the continent. This was just another job. But this bridge was different. This bridge was already carrying more weight than it was designed to support. And every rivet driven, every beam hoisted, every ton of steel added made the situation worse. The compression members, the lower cords running the length of the bridge, were bearing stresses that exceeded any established by past practice. The latticing holding these massive pieces together was inadequate for the loads it was experiencing. The camber, the slight upward curve built into the cords to account for deflection under load, was disappearing as the steel bent under forces it wasn't designed to withstand. And in New York, 700 miles away, Theodore Cooper sat in his office, reviewing drawings and telegrams, trusting that everything was fine. It wasn't fine. June 19. 07. Norman McClure saw the problem first. McClure was a young engineer, barely 30 years old, serving as Cooper's on-site inspector. He was essentially Cooper's eyes at the bridge, responsible for identifying and reporting any issues. In June, he noticed something disturbing. Some of the cord splices on the south anchor arm showed errors in alignment. The massive steel pieces weren't fitting together properly. They were being forced into position, bent and stressed to make the connections work. McClure wrote to Cooper, describing the situation and noting that corrections were being made. Cooper's response, recorded in the official correspondence, was dismissive. "It is not serious," he wrote. He remarked only that it would be well to draw attention to as much care as possible in future work to get the best results in matching all the members before the full strains are brought upon them. This telegram would be read aloud at the Royal Commission hearings 6 months later. The words, "it is not serious," would become evidence of negligence. But in June 1907, they were just another dismissal in a pattern that would kill 75 men. Translation: try to do better next time, but don't worry about it. August 6th, 1907. McClure noticed something worse. The lower cords on the south anchor arm were bent, not slightly misaligned like before, bent, visibly curved. These were compression members, designed to be perfectly straight to distribute loads evenly. Bending meant they were buckling under load, which meant they were failing. McClure telegraphed Cooper immediately. Cooper's response, preserved in the records, revealed his confusion. "How did that happen?" he asked, as if the steel had spontaneously deformed for no reason. He asked McClure to investigate, but took no immediate action. August 12th. McClure reported 2 more bent cords. The problem was spreading. The deflection was increasing. John Deans, the chief engineer on site, insisted that work continue. The contractual deadline was looming. Delays meant penalties. They couldn't stop construction every time someone saw a bent piece of steel. But some of the Phoenix Bridge men on site were becoming alarmed. Yenser, the foreman, believed the situation was critical. The steelworkers could see the deflection growing. They could feel the structure shifting under them as more load was added. Something was wrong, and everyone on the bridge sensed it. Burks, the superintendent, refused to acknowledge the severity. He insisted the bends had been in the members from the beginning, that the steel had arrived from the fabrication shop already deformed. It was a manufacturing defect, not a structural failure. This position was comforting because it meant the bridge wasn't actively failing. The steel was just imperfect. They could work around imperfect steel. McClure didn't believe it. He'd inspected these cords when they were installed. They hadn't been bent then. The deflection was new, and it was increasing. He wrote to Cooper again, stating explicitly, "Although a number of the cords originally had ribs more or less wavy, as I have reported to you from time to time, it is only very recently that these have been in this condition, and their present shape is undoubtedly due to the stress they are now receiving." The bridge was buckling under its own weight. Later, forensic engineers would calculate that by this point, the compression members were experiencing stresses 30% higher than they were designed for. The bridge wasn't slowly failing. It was in a state of progressive collapse, shedding load from failed members onto adjacent members that couldn't handle it. The question wasn't if it would fall. It was when. Between August 7th and August 27th, telegrams, letters, and telephone calls flew between Quebec City, Phoenixville, Pennsylvania, where Phoenix Bridge had their headquarters, and New York, where Cooper maintained his office. McClure was insistent. Cooper was concerned, but distant. Deans wanted to keep building. Schlapke, who had designed the failing members, was defensive. And every day, 86 men climbed onto a bridge that was slowly, visibly, catastrophically failing. August 27th. McClure measured the deflection again. It had grown. The bend in the compression cords was now plainly visible to anyone who looked. The camber that had been built into the steel was gone, replaced by a downward curve. The members were no longer resisting the load. They were yielding to it. McClure sent another urgent message to Cooper. This time, finally, Cooper recognized the severity. He telegraphed the Phoenix Bridge Company in Phoenixville with a clear directive. Add no more load on Quebec Bridge until all facts considered. Then he told McClure to immediately board a train to New York to discuss the situation in person. McClure was to travel to Phoenixville afterward to meet with Phoenix Bridge officials. The telegram was sent at 12:16 p.m. It arrived at Phoenix Bridge Company's offices in Phoenixville at 1:15 p.m. But Phoenixville was not Quebec City. The message sat in the office. No one immediately relayed it to the construction site 700 miles north. Communication in 1907 was primitive by modern standards. Telegrams went to offices, not construction sites. Someone would need to take the message, recognize its urgency, and send it on to Quebec by telegram or telephone. No one did. McClure, meanwhile, boarded a train in Quebec City and traveled overnight to New York. He arrived on the morning of August 29th and went directly to Cooper's office. For the first time, Cooper grasped the full magnitude of the crisis. The bridge wasn't just slightly overstressed. It was actively failing. The compression members were buckling. The structure was in immediate danger of catastrophic collapse. Cooper told McClure to telegram Phoenix Bridge immediately, ordering them to stop all work on the bridge. McClure sent the telegram. Then, Cooper sent him to Phoenixville to discuss corrective measures. McClure wouldn't arrive in Phoenixville until 5:30 p.m. In Quebec City, 700 miles north, it was a hot August afternoon. The sun beat down on the steel structure, expanding the metal, adding thermal stresses to an already overstressed system. 86 men worked on the bridge, unaware that a stop work order had been issued hours earlier, unaware that the designer finally understood the bridge was failing, unaware that they had minutes left. Beauvais drove rivets into the southern span. A rivet he'd driven an hour earlier had snapped. He called out to his foreman, and the bridge screamed. The sound came first. Not a crack or a snap, but a scream. The sound of steel tearing, of rivets shearing, of lattice work collapsing, of every connection failing simultaneously. Workers later described it as the sound of the world ending, a metallic shriek that froze every man on the structure in place for a half-second of pure terror before the deck beneath them disappeared. 5:30 p.m., August 29th, 1907. The lower cord in the anchor arm near the main pier, designated a 9 allonge, L buckled completely. The compression member, already bent beyond its capacity, surrendered to physics. When it failed, it shed its load instantly onto adjacent members, which were already at their maximum capacity and could not absorb the additional stress. They failed in sequence, a cascade of destruction propagating through the structure faster than human reaction time. The south arm and part of the central section dropped. 15,000 tons of steel fell 700 feet into the St. Lawrence River in 15 seconds. Men didn't have time to scream. One moment they were driving rivets, walking beams, checking connections. The next moment, the structure beneath them was gone, and they were in free fall, surrounded by a storm of steel. Beauvais, the riveter who had seen the snapped rivet, fell with the bridge. He plunged into the St. Lawrence, surrounded by debris, into water churned white by the impact of thousands of tons of metal. Somehow, impossibly, he surfaced. He was wounded, his leg broken, but alive. He managed to wriggle free from the twisted wreckage and was pulled from the water by a rescue boat. The timekeeper, a man named Hewitt, had been preparing to blow the whistle, signaling the end of the work day. He felt the deck collapsing beneath him and ran. The superstructure was falling in sequence, collapsing from the riverside toward Port Shore. Hewitt ran faster than he'd ever run in his life, racing the destruction, feeling girders snapping behind him. He reached solid ground as the last girder collapsed inches behind him. He lived because he'd been standing on the right part of the bridge when it started to fall, and because he'd run in the right direction, and because he'd been fast enough. The locomotive engineer wasn't so lucky. A work train sat on the bridge, its locomotive weighing several tons. When the bridge fell, the locomotive plunged into the river. The engineer went down with it, trapped in the cab as it sank. A rescue boat reached the partially submerged wreck and somehow pulled him free. He was one of 11 men recovered alive from the collapse. 75 men died. Some were crushed instantly by falling steel. Some fell 700 feet to the water, which at that velocity was as hard as concrete. Some drowned, trapped in the wreckage, pulled down by the current, unable to reach the surface. Some were caught in the twisted metal, pinned by beams, their bodies visible but unreachable as the debris settled into the riverbed. Rescue workers could hear them screaming. Michel Lebreu, who authored a comprehensive history of the bridge, documented the rescue attempts. The tide was low. The river was shallow near shore. Some workers were trapped, but still alive in the crumpled metal. Rescue workers tried desperately to free them, working with saws and cutting torches. In some cases, they had to make impossible choices. To free a man whose leg was pinned, they cut off his leg. To reach another whose arm was trapped, they amputated his arm. The men screamed as they were cut free, but at least they lived. Others weren't so fortunate. Some bodies were never recovered, buried under 15,000 tons of steel that would take 2 years to clear from the riverbed. Of the 75 dead, 33 were Mohawk steelworkers from Kahnawake. The reserve had sent its best skywalkers to the Quebec Bridge, men who worked without fear at heights where others trembled. Now they were gone, and the reserve faced a loss that would echo for generations. They were buried at Kahnawake under crosses made from steel beams, a permanent reminder of the price paid for someone else's engineering failure. In Quebec City, 10 kilometers away, people felt the ground shake and feared an earthquake. The collapse had released energy equivalent to a significant seismic event. The sound carried for miles. People ran to windows, looked toward the river, and saw a mushroom cloud of dust and spray rising from the St. Lawrence. The Quebec Bridge, which was supposed to be the engineering marvel of the age, had become 15,000 tons of scrap metal in the river and 75 coffins. At 5:30 p.m., Norman McClure arrived at Phoenix Bridge Company's offices in Phoenixville, Pennsylvania. He'd been traveling all day, first overnight from Quebec to New York, then from New York to Phoenixville. He was there to discuss how to save the bridge, how to reinforce the failing members, how to prevent disaster. He walked into the office and learned the bridge had collapsed 4 hours earlier. The telegram Cooper had sent at 12:16 p.m., ordering all work stopped, had arrived in Phoenixville at 1:15 p.m. It had never been forwarded to Quebec. McClure's second telegram, sent from Cooper's office that morning, had presumably also arrived. Neither message had reached the men on the bridge. If the first telegram had been immediately relayed to Quebec, there was a chance, however small, that the bridge could have been evacuated before 5:30 p.m. The men might have lived. Instead, they died because a message sat in an office for 4 hours, unforwarded. And 75 men paid for that assumption with their lives. But this wouldn't be the last time the Quebec Bridge killed. 9 years later, after every lesson had been learned, after the world's best engineers had redesigned everything, it would happen again. In front of 100,000 spectators. We'll get to that horror. First, the investigation. Harper's Weekly, one of the leading publications of the era, published a searching question that captured public horror. Was it properly constructed? Was the iron of inferior quality? Is there no method of making iron bridges of assured safety? And who is responsible, so far as responsibility goes, for such an accident? The engineer who designed the bridge, or the contractor, or the builders, or the railroad corporation? Canada wanted answers. August 30th, 1907. One day after the collapse, King Edward VII authorized a royal commission of inquiry. 3 engineers, Henry Holgate of Montreal, J.G.G. Carey from McGill University, and Professor John Galbraith from the University of Toronto. They had full powers to summon witnesses and compel testimony. They visited the site immediately. They interviewed survivors. They traveled to New York to interrogate Cooper for a week. They went to Pennsylvania to grill Phoenix Bridge officials. The investigation was exhaustive. The commissioners examined every decision, every calculation, every communication. They reviewed the specifications, the design drawings, the load calculations. They brought in additional consulting engineers to verify their findings. They tested specimens of the failed steel to ensure the material itself wasn't defective. The steel was fine. The problem was the design. The Commission's report, delivered in full on February 20th, 1908, issued 15 conclusions. The most damning were simple and direct. The collapse of the Quebec Bridge resulted from the failure of the lower cords in the anchor arm near the main pier. The failure of these cords was due to their defective design. The design of the cords that failed was made by Mr. P. L. Schlapke, the designing engineer of the Phoenix Bridge Company. This design was examined and officially approved by Mr. Theodore Cooper, consulting engineer of the Quebec Bridge and Railway Company. The failure cannot be attributed directly to any cause other than errors in judgment on the part of these two engineers. These errors of judgment cannot be attributed either to lack of common professional knowledge, to neglect of duty, or to a desire to economize. The ability of the two engineers was tried in one of the most difficult professional problems of the day and proved to be insufficient for the task. The Commission's words were carefully chosen. Cooper and Schlapke weren't accused of negligence or corruption. They were simply insufficient. They had attempted something beyond their capability, and 75 men had died because of it. The report continued. The failure on the part of the Quebec Bridge and Railway Company to appoint an experienced bridge engineer to the position of chief engineer was a mistake. This resulted in a loose and inefficient supervision of all parts of the work on the part of the Quebec Bridge and Railway Company. In their most cutting assessment, the commissioners wrote, "It was clear that on that day the greatest bridge in the world was being built, without there being a single man within reach who by experience, knowledge, and ability was competent to deal with the crisis." 75 men died because the people in charge weren't competent to recognize an emergency until it was too late. Theodore Cooper, the proud, even arrogant engineer who had designed bridges for decades, gave extensive testimony. His words, recorded in the journals of the day, revealed a man attempting to deflect responsibility while maintaining professional dignity. "I had and have implicit confidence in the honesty and ability of Peter Schlapke, the designing engineer of the Phoenix Bridge Company, when I was unable to give matters the careful study that it was my duty to give them. I accepted the work to some extent upon my faith in Mr. Schlapke's ability and probity. When pressed about the future of bridge engineering and what lessons could be drawn, Cooper's response was telling. My responsibilities, gentlemen, end as soon as I have served my duty of aiding you in reaching the truth in regard to the destruction of this bridge." He was done. He would accept no further questions about what should happen next. His career was over. Cooper and Schlapke escaped criminal charges. The Commission ruled their errors were judgment, not negligence, but their reputations were destroyed. Cooper withdrew from practice, living out his final years in isolation. John Deans, who had insisted work continue, eventually became vice president of Phoenix Bridge Company. The workers were dead. The engineers lived. The site of the collapse became a pilgrimage destination for engineers from around the world. They came to study the wreckage, to examine the failed members, to understand the mathematics of catastrophic failure. the twisted steel became a classroom, teaching lessons written in blood. Engineering textbooks would study the Quebec Bridge for decades. The phrase rules of thumb, the traditional engineering practices based on experience rather than rigorous mathematical analysis, became suspect. 20th century engineers would thereafter depend on far more rigorous applications of mathematical analysis. The Quebec Bridge collapse changed how bridges were designed, reviewed, and supervised. But the story wasn't over. Because Quebec City still needed a bridge. The economic imperative hadn't changed. The railway still ended at the St. Lawrence's edge. Montreal was still pulling ahead commercially. Something had to be built. The Canadian government took over the project entirely, providing full funding and oversight. They appointed a 3-engineer board to redesign the bridge from scratch. The board consisted of H.E. Vautelet, a former Canadian Pacific Railway engineer serving as president and chief engineer; Maurice Fitzmaurice from Britain, who had worked on the construction of the Firth of Forth Bridge; and Ralph Modjeski from Chicago, one of America's leading bridge engineers. These were not men of insufficient ability. These were the best bridge engineers in the world, and they knew the stakes. Engineering News wrote of their task. The progress and results will certainly engage the most careful attention of the engineering world. As matters actually stand, this attention will be multiplied by the stimulus of the intense interest awakened by the collapse of the first bridge. There will be a more anxious, more rigid scrutinizing of the conclusions and the designs produced by the committee. They designed a new bridge with a single cantilever span like the original, but this one would be massive. Where Cooper's bridge had weighed 325 meganewtons, the new bridge would weigh 2.5 times as much. Every component was overbuilt. Every calculation was checked and rechecked. Nothing would be assumed. Everything would be tested. The board made its own independent design, then compared it with the design produced by the St. Lawrence Bridge Company, the new contractor. Any discrepancy was discussed exhaustively and resolved. They tested quarter-scale compression members at Phoenix Iron Works to verify the designs would work. One major change differentiated the new construction plan from the original. Instead of building the suspended span in place, cantilevering it out over the water, as had been done before, they decided to build the center span off-site, float it into position on barges, and lift it into place in one piece. This would reduce the stresses on the cantilever arms during construction and allow the suspended span to be inspected thoroughly before installation. By 1916, the new bridge was nearing completion. The anchor arms and cantilever arms were in place, massive structures that dwarfed the failed first bridge. The center span had been completed and sat on barges in the St. Lawrence, a 5,000-ton section of steel ready to be lifted into its final position. September 11th, 1916, the lift was scheduled. Engineers, government officials, and the board members were present to oversee the operation, and 100,000 spectators gathered to watch history being made, the completion of the world's longest cantilever bridge. The crowd included Lomer Gouin, the Premier of Quebec, and Sir Wilfrid Laurier, the federal opposition leader and former Prime Minister. This was a moment of national pride. After 9 years and $25 million, after every lesson had been learned and every precaution taken, Canada was about to complete what had seemed impossible. The lifting operations began at 10:30 a.m. Hydraulic jacks at each corner of the suspended span began raising it slowly, carefully, toward its final position 150 feet above the water. Engineers monitored the operation constantly. The lift proceeded smoothly. After the first lift, pins were inserted connecting the lifting links to the fixed jacking girders, transferring the load directly to the cantilever trusses. The jacks were released and lowered for another lift. Everything was going perfectly. At 10:50 a.m., a sharp report was heard. The sound was distinctive, unmistakable, metal failing under stress. The southwest corner of the suspended span tore away and sagged. For a moment, perhaps 2 seconds, the massive steel structure hung at an angle, supported on 3 corners while the fourth pulled free. Engineers stared in disbelief. This couldn't be happening. Every calculation had been checked. Every component had been tested. This was impossible. Then the other corners pulled off their supports. The entire suspended span, 5,000 tons of steel, came loose and disappeared into the St. Lawrence River. 100,000 people watched it fall. They had come to witness triumph, and instead witnessed disaster. The span hit the water with a massive splash, throwing spray 200 feet into the air. It sank immediately, settling into the river beside the wreckage of the first bridge, which still lay on the riverbed after 9 years. 13 men were carried to their deaths. 14 others were injured. Unlike the first collapse, where there had been few eyewitnesses, and the disaster occurred at the end of a work-day, this collapse happened in full view of a crowd that included engineers, journalists, government officials, and photographers. Engineering News reported that many prominent engineers from the United States and Canada were on the suspended span when the lifting operations began. At the intermission in the jacking operations, they came ashore. That saved their lives. The engineers who had been inspecting the lift during the first raise had left the span when the jacks were lowered for repositioning. That decision saved their lives by minutes. The 13 men who died were workers who had remained on the span, presumably checking connections or preparing for the next lift. Immediately, fears of German sabotage were reported. World War I was raging in Europe. German agents were known to be operating in North America. The timing seemed suspicious. A major national project destroyed just when victory was in sight. Newspapers speculated. Officials investigated. Within 24 hours, it was clear that sabotage had nothing to do with it. This was another engineering failure. The exact same pattern as 1907, just compressed into a smaller time frame. They'd learned nothing. The investigation found the cause within hours. A steel casting at the southwest corner, designed to transfer the span's weight to the lifting apparatus, had broken. When it failed, the entire 5,000-ton span slid off its supports. The chief engineer, H.E. Vautelet, had been made aware of a potential problem 6 weeks before the collapse. Franz Lichtenberg, the engineer responsible for the construction of the center section, who was also working as an inspector for the federal government, had raised concerns about the casting design. His warnings had been noted, but not acted upon. The failure occurred exactly where he had predicted it might. Once again, warning signs had been ignored. Once again, men died. The difference this time was that the error was localized. The bridge design itself was sound. The massive cantilever arms, built to hold twice the load of the first bridge, had performed perfectly. The problem was a single component in the lifting apparatus, a casting that hadn't been adequately designed for the stresses it would experience. Quebec Bridge had killed again, but at least the lesson was narrower. The government granted special permission for the bridge builders to acquire the needed steel to build a third center span, despite wartime shortages. Steel was in high demand for the war effort, but the Quebec Bridge project was deemed essential. Reconstruction began almost immediately. This time they used a stronger casting design. This time the lift was monitored even more carefully. This time every possible failure mode was considered, tested, and accounted for. August 1917. The third center span was completed and successfully lifted into position without incident. The Quebec Bridge was finally, after 30 years of planning and construction, after 2 catastrophic collapses, after 88 deaths and countless injuries, complete. December 3rd, 1919, the Quebec Bridge officially opened for rail traffic. August 22nd, 1919. The Prince of Wales, later King Edward VIII, formally dedicated the completed structure. Theodore Cooper, the proud engineer, whose design had killed 75 men, died 2 days after the dedication ceremony. Whether he attended the ceremony is not recorded. Whether he felt vindication that the bridge was finally complete, or shame that it had cost so many lives, is unknown. He took his thoughts to the grave. The Quebec Bridge stands today, 106 years after its first collapse. It remains the longest cantilever bridge span in the world at 549 meters. A record that will likely never be broken because cantilever design has been superseded by more efficient suspension and cable stay designs. It's a massive structure, 987 meters long, 95 meters wide, 104 meters high. It accommodates 2 sets of railway tracks, 2 sets of streetcar tracks, and 2 roadways. By 2015, 60% of the bridge was covered in corrosive rust. The monument that cost 88 lives to build needed $200 million more just to keep standing. August 29th, 2006. 99 years after the first collapse, a year-long commemoration began in the Kahnawake Reserve for the lives of the 33 Mohawk men who died in 1907. August 29th, 2007. 100 years to the day after the disaster, memorial services were held to dedicate a concrete structure displaying the victims' names on the Levy side of the bridge. In Kahnawake, a steel replica of the bridge was unveiled, a permanent memorial to the skywalkers who never came home. The names are recorded now, preserved, remembered. 33 Mohawk men, most in their 20s and 30s, who went to work one August morning and fell 700 feet to their deaths because someone in New York made a calculation error and someone in Pennsylvania didn't forward a telegram. Their crosses, made from steel beams taken from the collapsed bridge, still stand in Kahnawake. Iron crosses for iron men who died in iron. The Quebec Bridge disaster gave birth to a Canadian engineering tradition. Many graduates receive an iron ring during the ritual of the calling of an engineer, worn on the little finger of the working hand. The rings were once said to be made from steel taken from the collapsed bridge, though this is likely legend. But the symbolism is powerful. Every time a Canadian engineer drafts a design or signs off on calculations, the ring is there. A reminder that errors in judgment have consequences measured in human lives. The Royal Commission's report became one of the pioneering documents in the field of forensic engineering. It established protocols for investigating structural failures, demonstrated the importance of independent peer review, and showed how organizational failures can be as deadly as technical ones. The collapse changed everything. Modern bridges require on-site supervision with authority to stop work. Engineering codes replaced optimistic guesswork with rigorous testing. The rules of thumb that built 1,000 bridges went down with the Quebec Bridge. But perhaps the most important lesson was about communication. The telegram that might have saved 75 lives sat in an office for 4 hours because no one took responsibility for forwarding it. In an emergency, minutes matter. The assumption that someone else will handle it kills. Modern projects have redundant communication systems, clear protocols for emergency messages, and defined responsibilities for safety-critical information. If a stop work order is issued, multiple people verify it was received. No message sits in an office while men work in danger. These lessons came at a terrible price. 88 men died teaching them. 75 in 1907, 13 in 1916. Each death was preventable. Each death resulted from a failure of human judgment, human communication, human pride. The mathematics were available. The warning signs were visible. The knowledge existed. What failed was the willingness to admit error, to accept that the bridge was beyond the designer's abilities, to choose lives over economy and safety over reputation. The Quebec Bridge stands as a monument to these failures. It's a bridge, yes. Still carrying traffic after over a century, but it's also a massive steel tombstone, marking the graves of 88 men who trusted that someone had done the math correctly. Every bridge engineer knows the Quebec Bridge story. Every structural engineering student studies the failure modes. The collapsed compression cords are analyzed in detail. The communication failures are dissected. The organizational problems are examined. It's required learning because the lessons are too important to forget. But knowing the story and truly understanding it are different things. Theodore Cooper had built bridges for decades. He'd written the standards, but he didn't understand that past success doesn't guarantee future safety. He designed a bridge 18% heavier than his calculations assumed, accepted stresses that exceeded all established practice, and supervised construction from 700 miles away. Each decision made sense alone. Together, they were fatal. The first time the bridge fell, 75 men died. The second time, after every lesson had supposedly been learned, after the best engineers in the world had redesigned everything, after every calculation had been checked, 13 more men died. The bridge that was supposed to make Quebec City an economic powerhouse became the bridge that killed twice. The engineering marvel became an engineering horror story. The longest cantilever span in the world became the deadliest bridge construction project in history. And somewhere in the St. Lawrence, buried under the mud and silt of over a century, 15,000 tons of steel from the first bridge still rest on the riverbed. A monument to ambition, arrogance, and the price of error. The bridge above it carries traffic every day, trains and cars crossing the river without knowing what lies beneath. Most people who cross don't know the story, don't know about Beauvais and his snapped rivet, don't know about McClure's unheeded warnings, don't know about Cooper's telegram that arrived too late, don't know about the 33 Mohawk skywalkers buried under steel beam crosses. But engineers know. Every engineer who has touched an iron ring knows. Every structural engineer who has designed a bridge knows. Every project manager who has faced a deadline and been tempted to ignore a warning sign knows. The Quebec Bridge stands as a reminder. It stands as a warning. It stands, quite literally, on the bodies of 88 men who trusted that someone had done the math correctly. They built it to last a century. It collapsed twice before it opened. And that difference between intention and reality, between design and execution, between pride and prudence, is written in steel and blood across the St. Lawrence River. The longest cantilever bridge in the world. The deadliest bridge construction disaster in history. The bridge that killed twice.